Welcome back to DCG. Okay, what we're working on here today is a series on skew lines. We were mentioning in class today that if you look at right angles to a particular line, you will see it as a true length. Another way of finding that true length is to rotate it around so that it's parallel to the XY line, which effectively means you're looking at right angles. It's the same thing again. Our heights are taken from the elevation, because any object that is a meter high in elevation, no matter what elevation you take it from, it will always remain a meter high. If you look down along that true length, you wind up seeing that as a point view. Now that will be very important for us later on. So there's two things I want you to notice here. One, you're looking at right angles to AB in the plan. That gives you a true length, A2, B2. And when you look along that true length, you get a point view. That red dot down on the bottom is A3, B3. Now this is where we started off today, and we were saying that the two lines, sorry, jumped ahead there, the two skew lines on the right hand side are truly skew lines because they do not meet the intersection point in the elevation, does not correspond to the intersection point on the plan. Now let's just go through this slowly. We have this point up here we refer to as point M today. DM is parallel to AB. DM down here on the bottom is parallel to AB. It's a horizontal line across here. CM is a horizontal point. And C to here. Once I drop down this blue line, I get this point here, point M. CM is a true direction and a true length. It's a true direction because it's the direction of a horizontal line, and it is the true length because it is a horizontal line. I've made it horizontal up here. I'm looking at right angles to it in the plan. So if I look at right angles to something, i.e. straight down on top of it, this here will be a true length. Now that's important because when I look at along that, I get the point view of that line. The point view of that line gives me the edge view of the triangle of which it is a part. Okay, and because this line and this line, AB, are totally parallel, truly parallel, they're truly parallel up here, they're truly parallel, then they will have to be truly parallel down here. Same thing again. This time I'm moving one step forward. I want to find the shortest perpendicular distance. So I am looking at right angles to these two lines. And I project all those points up there, and these measurements, the distance from there to A3, okay, is taken from there back to A, okay, and the distance from here to D3 is taken from here back to D. That is the projection of my shortest distance. I project that back up to my plan, and this is the shortest distance transferred to the elevation. Moving swiftly along. I'm moving at speed here. You can slow it down at any stage if you wish yourself. Looking at right angles to CD shows me CD as a true length. Looking along CD, which is the second blue arrow down along here, is going to give me CD as a point view. The shortest perpendicular distance between the two is shown up there in red, and obviously I can project that back in. Next up, we have the shortest horizontal distance. And because the blue arrow is parallel to the XY line, which is the same as this XY line up here, that is vertical distance, that is a vertical distance. This here is horizontal because it's parallel to this. There's the position of my intersection point, and return back up to their two views. Notice that this one here is also horizontal. It's the only time it will be horizontal because I'm looking for the shortest horizontal distance. This one here is the shortest distance at a particular angle. Now it might look like that's close to 90 degrees, but it's not. What I'm looking here is the line of sight at a particular angle. That may be 35 degrees, 41 degrees, whatever. But whatever it is, I'm looking along that line. And that's where I project out this way. Again, I'll get my point of intersection, project that back in, and that is the shortest distance at a given angle. Now I'm absolutely screaming through this stuff here. This is where we were this morning, and we said we were going to find out the true length of BC. The reason we want to find the true length of BC is if we look along that line, we will get the edge view of that plane. Take a line anywhere across, I find my true length and true direction, and I indicated to you this morning that I normally take the point from here, B, straight across, drop down. It will give you exactly the same thing. It's just that's one less line to project. Now I've got two planes here, one blue and one green. I'm taking on one of them only. It's only required on one of them for the moment. You'll see why. I get the edge view of one, which is the ABC plane. And I'm trying to find the intersection line between the two. And the intersection line between the two is taken back to the elevation and back to the plan. Same thing, only this time I'm taking a horizontal section. If I have the two planes, I will find that if I take a cut across there, I wind up with 2 points on each plane down here, on each triangle down here, and those will be two horizontal lines. Those two blue lines in plan are horizontal lines. They're horizontal lines because they're on this yellow surface over here. Repeat the same operation for the higher one, and the black line, as indicated here, is the line of intersection, and the same up there. Now this is where we finished up, and it was basically the dihedral angle between both. Now you've taken down the measurements for this question, so why don't you have a go at it tonight? We decided that we were going to look at right angles to CB, because CB is the line of intersection. CB is the line of intersection. If I look at right angles to it, and I can do this in either view, I will get CB as a true length. When I look along the true length, I will get a point view. And there's the dihedral angle in between these two laminae. Thank you and good night.